All right. It looks like we're just about assembled. It's a great pleasure to continue the morning session. We have Jeongwan Haah from MIT, and then Dave Gossett following afterwards. Take it away.
Thank you. Today I'm going to talk about sample optimal tomography of quantum states. This is a joint work with Aram and Zhengfeng and Xiaodi and Nankun. I believe Aram and Xiaodi is in the audience today. So I believe all of you must be familiar with tomography, but let's begin with a very familiar example. Suppose there's a president election in the world of animals, and we wish to know the outcome of the election prior to the vote. So we randomly select some of the population and ask what their opinions are, and we gather some statistics. Or if you are a geoscientist, then if you encounter an unknown rock, then you want to know the composition of that rock. And then what you do is you take pieces of that rock and you go to a composition analysis and make a plot to infer what the elements are there. This is basically the underlying probability distribution tomography. You want to know some uncertain thing with a good accuracy. Or if you are a quantum optics experimentalist, then perhaps everyday job is to verify that your experiment is going well. And sometimes your entire project is to verify that you have prepared very interesting state. So tomography is, well, the word tomography has a Greek root tomo that refers to sections. And graphy, of course, means a shape. So from a sectional measurement, you infer the shape of the original thing. In a quantum setting, you are provided with identical copies of a quantum state that is unknown to us, and then you make some measurement and you output the description of that state. You just want the matrix. That's the tomography. So our problem is very simple. Suppose you are given with a d-dimensional quantum state, completely arbitrary, except that it has some rank R. It can be pure state when R is 1, or it can be completely mixed when R equals D. And we demand some accuracy goal that can be measured in various ways, but here we address two types of distance measures. One is the trace distance, and the other is infidelity. This is just 1 minus fidelity, or if you're familiar with the Brest distance, this is a square of that. So the question is then, how many samples do you have to prepare in order to do a tomography to accuracy goal? And we ask, what's the scaling of that number of copies as a function of dimension and the promised rank and the accuracy goal? Okay, it's such a simple problem. Let's get warmed up with the classical probability distribution. In fact, it's not so hard calculation to compute the average error you make. So this is 1 minus fidelity. So the less the number is, you have more accurate value. The average error is upper bounded by this quantity. So whenever your sample number is greater than the probability space dimension D, then you have a very small average error. Therefore, it is less likely to make an error. It's less likely to make a wrong estimate. Or if you're using trace distance as your accuracy goal, then as a simple binomial calculation, you end up with the same answer. Here, the scaling looks different, but it's all because the distance measure is defined differently. It's not a fundamental thing. Actually, this thing is always greater than epsilon squared. Okay, and what about pure state? Previously, we talked about classical probability distribution, which is an example of general quantum state. And this time, we ignore the mixedness and just focus on the pure states. And it turns out that so-called symmetric POVM is the optimal way to do it. Here, symmetry means that we didn't assume anything about the underlying pure state. So we shouldn't distinguish this direction versus that direction. Our POVM's performance should not distinguish between the two. So the natural symmetric POVM that obeys that isotropic symmetry is just given by this. This is a continuous family of POVM, but for theoretical analysis, this is good. And for this setting, the infidelity and trace distance are basically equivalent. And actually, expected fidelity can be exactly calculated, or even higher moments of this average fidelity can be calculated. And it turns out that you only need d over that accuracy goal. Okay. So let's speculate what the answer should be. What's the number of copies? How does the number of copies should scale with respect to the error accuracy goal? Essentially, the tomography is the state discrimination procedure where you distinguish rho tensor n from, say, sigma tensor n. In that case, this inequality holds. This is a simple consequence from the relation between trace distance and fidelity. And if rho and sigma were, say, epsilon apart, if you are provided with n copies of them, then their distance is very close to 1. So the more copies you have, it's more likely that you will be able to distinguish them. And the rate at which the distinguishability approaches 1 is determined by the fidelity. So by this simple estimate, we infer that the necessary number should scale as 1 over that infidelity. If you have lesser number of that, then it is likely that you will be wrong. So you at least need that much. Here, I want to point out some difference between two distance measures. Trace distance has a very nice operational meaning that if you wanted to prepare, say, rho, but you accidentally prepare sigma where trace distance is close, then your final outcome will be just proportional to the trace distance between the two. But in this tomography setting, I would like to say that the infidelity is more proper measure in the following reason. So just focus on the probability distribution tomography. Say you want to measure some concentration of impurity. You want to measure that small number. In that case, well, we're theorists, so let's compare two simple states. One is just pure state, and the other is a slightly impure state. In that case, the trace distance between the two is just eta. Eta is this parameter, a small parameter. And the infidelity is also order of eta. In that case, from the previous analysis, we know that using the trace distance, we need to have 1 over eta squared number of copies, whereas this bound in terms of infidelity tells us that we only need 1 over eta. And because of Because of this scaling, we know that 1 over infidelity must be the right answer. So indeed, in this special regime where purity is very high, then trace distance gives you a much higher number than actually necessary. So in the tomography setting, infidelity is more important and more proper measure of distance. Okay, what about the number of copies scaling in number of parameters? Well, the quantum state that is d by d matrix, and if you're guaranteed that you have rank R, then there are approximately roughly R times d number of parameters because the matrix is a rectangle. So it's conjectural that that number of copies should be enough for fixed accuracy. But is that really true? It was unknown. So we answer that question. Oh, well, yeah. And the scaling of dimension dependence was witnessed in the probability distribution tomography or pure state tomography And our intuition is correct, that you really need the number of parameters that describes the state. In general, it was unknown, and our results confirms that intuition. So you really need that much. Suppose I have accuracy goal delta measured in infidelity, then you only need that much number of copies in order to estimate the state accurately. Or in terms of trace distances, the bound looks like this. And we have a matching lower bound that you must have that number of copies, the number of parameters divided by the accuracy goal. There's a small logarithmic factor, but up to that, they match. So this is optimal bound. I have to mention that there is a simultaneous and independent work. And they have computed the average error measured in 2 norm, actually. And the 2 norm can be as small as 1/square root of the rank of the matrix or compared to the 1 norm. So this reads like the number of parameters in the density matrix divided by the accuracy goal. Let me emphasize once again that this does not imply our bound in terms of fidelity. And we know that fidelity is more proper measure. But this bound is better in the sense that it does not have log factor in dimension. Actually, previously, the best available result was only appeared last year, where you need r squared times d over the accuracy goal. So if your state is order of full rank, then this scales like d to the cube, whereas new bound says it scales like d to d squared. So it's an improvement in dimension vector.
What distribution is this expectation thing over? So are these bounds for average over some ensemble states?
So,
what distribution is the expectation taken over? Are these supposed to be for some worst case row, or is it against some expectation?
You're given with some state, and your measurement cannot be always definite. So it will be some distribution, and this is the average of that experimental outcome distribution.
Also worst case over row.
Yeah. So let's get into how we get this result and what the measurement scheme is. Let's speculate what the measurement must be. So I said write POVM. So the input to the problem is just n copies of the same state row. So this has obvious symmetry that you can permute things around among the tensor factors, but that doesn't do anything. So it has true symmetry. And as I briefly said before, we shouldn't distinguish between row to the tensor n versus some rotate version of row tensor n, because we don't assume anything about the underlying state. So our POVM would better have symmetry that is permutation times the unitary matrix. It's a huge symmetry. And whenever we encounter a problem with a huge symmetry, we know what we should do. We should go into the basis where the symmetry action is diagonal. And that comes under the name of surevie duality in the representation theory. So let me briefly tell you what that is. Our Hilbert space is just n copies of Q dits, right? And we know that the permutation group just acts by permuting tensor factors. So in the basis factor, it looks like A tensor, B tensor, C tensor, D goes to some permutation of them. And the unitary group acts on this space by the simultaneous rotation of all components. And the theorem is that these representations are mutual commutants. So let me be more precise. The calligraphic A stands for all the matrices that represents the permutation group. Then if you take a commutant, that namely all the matrices acting on the Hilbert space that commutes with that representing matrices, then it turns out that that commutant is equal to the linear span of matrices spanned by the representing matrix of this unitary group. And the converse is also true. So they are maximally commuting set of symmetries on the full Hilbert space. And one consequence of that being a mutual commutant is that if you decompose this full Hilbert space into irreducible representations of the product group, then you always encounter one-to-one corresponding irreducible representations of each component group. And the representation of the symmetry group is conveniently labeled by these partitions. I'll get to that later. And you can slightly generalize the fact that there are being mutual commutants to the representation of general linear group, not only restricted to the unitary group. General linear group is not often discussed in the physics literature because it is not compact. And what does it mean to rotate by a general linear transformation? It has no physical significance. But for mathematics, it's very convenient because GL, the general linear group, is dense in the all set of matrices. So our decomposition can be used for any matrices that is of tensor product form. So in particular, we can represent the input state rho to tensor n as a direct sum of these representing matrices. Okay. A direct application of this decomposition, and in particular this expression, is appearing in the spectrum estimation. I said that the irreducible representation of the unitary group or the symmetric group is labeled by this so-called Young diagram. It's just a collection of boxes arranged in this form where you're not allowed to have more rows as you go down. It should decrease strictly or equal. And then the projector onto this irreducible component that has a large overlap with rho whenever lambda and rho have the very similar shape. And it's the only case that has a large overlap. So in expression, the rate at which this probability decays is exponential in number of copies. And if you have a large relative entropy distance between this lambda and rho, the lambda must be rescaled to match that it's just sum to 1. Then this inequality holds. And this was pointed out by Carr and Werner, and they used to use this machinery to estimate the spectrum of rho. Spectrum is a property of the density matrix that is, by definition, invariant under the rotations. And this representation clearly captures that, especially the projection onto the ERAP. So they pointed out that that can be used to measure the spectrum. And this probability bound actually tells you that this much sample suffices. It's rather surprising because there's a dimension factor squared, whereas we only have d parameters to describe the spectrum, but we actually don't know whether we can achieve without that square factor yet. But anyway, this gives a sample complexity for a spectrum estimation.
So I have to say that I really enjoy what you're saying, but I'm a little confused how this contrasts with the earlier POVM that you put up on the board, on the wall there. So what's the big conceptual difference from this measure over many copies of pure states?
Many copies of pure states?
Well, yeah, so you had for the pure state case this POVM, which was a tensor product of the same pure state n times, right? So there's some obviously symmetric and obviously that over that measure under UD equivalent. So kind of curious what What's the part here that's different? Yeah.
So, yeah, maybe I got confused you, but I did not give you my POVM yet. So the previous pure state POVM was designed to measure the direction of that pure state. Here, we forget completely about that direction and just focus on the spectrum. And the previous pure state POVM actually decomposition of one particular direct sum component of this composition. Yeah, and recently, O'Donnell and Wright actually improved to remove this log vector in trace distance again. So we still don't know whether this can be done in the infidelity. Okay, another ingredient of our construction for measuring the state is so-called pretty good measurement. This is a technical term, pretty good measurement. So this is defined as follows. We are provided with an ensemble of mixed states with some probability pi, and let's just define the positive operator in this funny way. This may be counterintuitive because the state is something that we measure about, and POVM element is supposed to extract number out of, and physically POVM elements are observables. But here we're mixing two concepts here by just exploiting the fact that density matrices are positive. But it turns out that this works very well. It's pretty good. Barnum and McNeil around 2000 showed that if you want to distinguish among this ensemble, then this POVM defined through this funny formula performs almost as good as the optimal one. The probability that you will have a correct answer to distinguish among sigma will be lower bounded by the optimal probability squared. So if you are in the regime of probability close to 1, then they just differ by at most factor of 2. And this later pointed out that if you have an arbitrary collection of the states and you are to distinguish among those states, then this indeed performs well, and the number of copies you need scales like logarithmic of total number of states. Okay, let's combine those two. So our scheme is that you make spectrum estimation first, and then you implement that pretty good measurement. And combining in equation, our POVM element looks like this. Pi lambda is the projection onto the irreducible component. And this looks like a state that has information about which direction you're in. And the spectrum of that state is just related to lambda in a direct way. And using this simple lemma that involves the character of the unitary representation, we get the result that the average, the probability that you will have a wrong answer from the true state will be pretty small if n is large. So in particular, if n is of order r times d over delta up to a log factor, then you have a very small probability of being wrong. So you will mostly succeed. And here's the amusing fact that proving this lemma only takes about this much. This is the direct copy of our paper. So our proof is pretty simple. And what about lower bounds? What's the limitation of tomography? So the rank R states form a manifold of states of real dimension roughly R times d, because there are R times d number of parameters. So we focus on, we imagine the manifold states as a just Euclidean space. And the crucial observation is that if you had a tomography apparatus, if you build up your lab with very good accuracy, that enables to transmit this much bits, because you can distinguish the 2 points on your manifold, and in order to describe 1 point in the manifold, it requires e times t bits. So technically, we actually zoom in further into this manifold to observe that, to forget about the global structure of this complicated manifold of states. So by saying manifold, I already declared that the small neighborhood of some state, it looks like a plain Euclidean space. And if you further zoom in, then there would be exponentially many states, exponential in dimension, many states that are separated by, say, some constant fraction of the original neighborhood size. So we utilize that fact. And in order to find sufficient number of many states in the manifold of states, we make use of the probabilistic existence argument. So you give me a state, and I randomly rotate it. How odd it is that I will encounter a very close state if you're in a very high dimensional space. So in particular, if I consider a epsilon diameter ball of the states, and I pick a particular, say, this dot, and I randomly rotate around that local region, how odd it is to encounter this ball that is epsilon, say, over 10, close to original state. This is very odd. Actually, it happens only with probability that is exponentially small in the number of parameters. So inverting that probability, you're guaranteed that you will have exponentially many states that are epsilon over 10 separated in that epsilon ball of states. And for this result, we make use of the random projection lemma. Okay, so how would we combine them? Another ingredient for the lower bound is that the Holevo theorem. Let me remind you what that was. So Alice prepares some index I, and then she sends over, say, sigma I according to that label I. And Bob is supposed to run the tomography procedure to infer what the I was. And the mutual information after Bob makes a measurement, that cannot be greater than the original mutual information presented in this state. And if you compute the mutual information in that state, that becomes the so-called Holevo pi quantity. And the colloquial interpretation of that theorem is that ensemble of states can only transmit that much bits. It's a quantitative theorem, very powerful. Okay, so quoting this theorem, we prepare many states that are separated so that your tomography procedure can distinguish them. And the set of states we choose, the epsilon neighborhood we choose from those large number of states is actually of this form. So it's very easy to compute explicitly the Holevo pi quantity for this ensemble. And it turns out that it is of order epsilon squared, where epsilon is that parameter. It's intuitive because if your states are too close by, then in the limit of epsilon goes to 0, you shouldn't be able to transmit any information. And using the probabilistic existence argument that we can find a large number of sets within that small ball, the mutual information between Alice and Bob must be lower bounded by a quantity that is proportional to the number of parameters. So combining these two inequalities, you get that your number of copies must be at least that much, which matches the upper bound up to logarithmic factors. Okay, I have delivered the idea completely. So we study the tomography problem where you're provided with the same copies of quantum states, and you do some measurement and output the density matrix. And the number of samples you need is number of parameters divided by the accuracy. Up to logarithmic factor, this is optimal. We have not addressed any problem with the implementation. We just cook up some POVM that matches this upper bound, but we have almost no idea how to efficiently implement this POVM. Having a continuous family of continuous POVM is not a problem because you can always discretize them, but it's unclear whether we can implement this POVM even on a quantum computer. And of course, more practical problem in this regard is that how well an adaptive measurement can perform. In this respect, the work by Khan and Gota is very relevant, where they studied the statistical ensemble of some small neighborhood set of states. They showed that if the neighborhood is small enough, then they just look like an ensemble of Gibbs state of simple harmonic oscillators. So analyzing that geometry of states more carefully will give us more definitive answer, may give some definitive answer to this question. And using the correspondence between a state and the channel, you can also apply this scheme to channel tomography, but this gives a quite it seems gives us some quite loose bound on the number of necessary use of channel. And of course, if we had some prior information about the state, well, here we assume nothing. We just given with the state, and that was it. And yeah, this is completely, extremely general problem, so we do not address here, but certainly it is an interesting area. Thanks.
So I'm curious, have you thought about the case where the rank R is not a priori known? In other words, if you don't know in advance that it's rank 1, rank 2, whatever, but in fact it is, how much of an advantage does that give you?
The current bound doesn't say too much about that. Well, I feel that's a very important question. How can you know the rank prior to measurement? Our answer to that is it's just d squared. So you have to assume R equals d. But I do believe that it can be improved. And using trace distance again, O'Donnell and Wright have achieved some results in that direction.
So, different question. Could I ask you to sort of comment as much as you'd like about the up to log factors? In particular, do you think those log factors are real? Do you think you can make them go away? And if you do think you might be able to make them go away in principle, where does the looseness come from in your proof?
Okay, I interpret that as a technical question. I believe it can go away. If you go through the similar analysis for the classical distribution tomography, if you compute the upper bound on the probability distribution itself, in particular the large deviation bound, then you encounter log factor again. But by directly computing average error, you get rid of the log factor. So maybe similar story is possible here. I am not sure. Yeah, that's my guess. And technically, our bound, our technique cannot remove the log factor because there is a factor of unitary irrep dimension, which inevitably involves a log n.
So in the middle of your talk, you made an argument that the infidelity was in some ways a better measurement than the trace distance. And you gave an example. I noticed in the example that you were looking at a mixture of two different states, for which the infidelity or fidelity is a good measure. But what about a small, a pure state that is slightly different than what you expect? The fidelity is not particularly sensitive to those kinds of errors.
Yes.
So, so is it possible that the argument that you gave, the bound for the trace distance was just sort of a loose bound? So I guess my question is the preference for using the trace versus the infidelity, does that more just have to do with the tightness of the bound that is known, or is it really more of a property of the distance measure itself?
So, well, more realistically, suppose you are actually measuring stuff and you are writing an experimental paper where you have to provide an error analysis. Then naive treatment with a trace distance will give you some error that's unnecessarily large. In particular, in those examples I provided, it happens then. So,
but is there possibly a better analysis that would give you smaller error bars?
Yeah.
Okay.
Yes.
So let's thank Jeongwan again.